Hi everyone, this is team number 1134, and this is our presentation on Problem A, Introducing Stress. We're all from George Fox University in Newberg, Oregon in the United States, and our team is made up of Honor, Paul, and myself, Jonah. Our mentor is Corban Harwood. Throughout all of history, productivity and efficiency have been two of the most highly desired qualities of a company. Getting this, though, is quite difficult, especially due to the presence of many variables. Factors such as a worker's stress level, their current capabilities, and the expectations placed on them all factor into their level of productivity. These factors are affected by nearly every aspect of life, making this process difficult to model. One example is a case in 2022, where a group of astronauts overestimated the amount of work they could get done, leading them to be overworked and overstressed. Our group has attempted to model a situation like this, where one capable but not experienced group of workers is introduced into a stressful situation, with another group currently working there. In doing so, we input three different equations for expectations into our model to determine the most productive way to place expectations on a new group of workers.
We have made a few assumptions to simplify our model for more general use. Firstly, we reduce a group's work output to be entirely dependent on time, stress, capabilities, expectations, and total work done. This means that other factors that might affect output are not considered here. The second assumption that we made was that we treated groups as single units, not as groups of people. This is because attempting to model each individual's characteristics would be impossible to do on a large scale, not to mention the interpersonal relationships within a single group that would affect a group's output. Finally, we have assumed that regardless of how stressed a person is, they become less stressed over time. This is not always the case, as people can begin to spiral downwards, overloading themselves. In that case, though, the work outputted would be zero, so there's no need to model it.
Before we got into our actual equations, our group thought it would be wise to analyze the function most of our own functions rest on, the logistic growth curve. Logistic growth is expressed as L divided by 1 plus e to the negative k times x minus x naught, where L is the maximum, x naught is the midpoint, and k is the logistic growth rate. We chose to use this for stress and capabilities because, firstly, we wanted to have an equation with a range of 0 to 1 so that we could represent stress and capabilities as a percentage, not as just some arbitrary value. Secondly, we wanted to highlight how these factors exponentially increase until you reach a point where it begins to slow down. For example, with capabilities, as you learn more, your capabilities exponentially increases until you get closer to mastering a skill, and then you don't gain as much from learning more about it. Our first set of equations are our equations for capabilities. We decided to have two equations for each category because we have two groups. For the first group that's already there, we decided to have capabilities equal 1. This is because they've previously done work there, they're experienced and capable, it makes sense to believe that they are fully capable at their job. For group 2, the one that's a bit capable but hasn't been there yet, we decided to modify the growth equation by putting C naught in front, which represents the amount of capability they have at base, which won't be 1 because they haven't done it before, but it also won't be 0 because they are capable of individuals. Then we put a 1 minus C naught on top of the logistic growth function, and we substituted in W of t for x and W naught for x naught, where W of t is our work equation. Stress is a bit more complicated due to there being more factors to mess with. Firstly, for group 1, we did 1 minus the logistic growth equation to represent how stress decreases over time. J is another logistic growth rate, but G and L are constants that show how long the first group has trained and worked there previously. We've also divided Euler's number by the two capabilities of the group multiplied together, representing how low capabilities mean that a group won't decrease their stress as quickly because they can't physically do the job. Additionally, we've added the stress of group 2 times a constant to group 1 stress, highlighting how if group 2 is stressed out, group 1 begins to worry about whether they can actually do the job. Group 2's equation is the exact same as group 1's, but it's minus the additional stress piece at the end and G and L. But it also has an extra tau times ET and subtracts tau from the 1. This value represents the amount of stress that a group has initially versus the amount of stress that a group gains due to the expectations being placed. A high tau means that most of the stress is derived from expectations, while a low tau means that most of the stress is because they just had it initially. For expectations, we created 3 different equations to model each of the 3 methods of placing expectations given in the guidelines. Each equation lands between 0 and 1, meaning that expectations can also be represented as a percentage. For E sub 1, full expectations are placed the entire trip, so the equation is a constant 1. For E sub 2, a period of rest is given before full expectations are placed, so we created a piecewise function to represent the 2 segments. Expectations are 0 until time reaches p, a value in days representing the length of rest. Expectations are then 1 until f, which represents the length of the entire trip in days. E sub 3 represents a gradual growth in expectations, beginning at 0 and increasing to 1 linearly. These 3 equations combine to give us an equation for the change in work with respect to time. Both of them follow the same format with some tweaks. They are expectations times capabilities minus stress. We've done 2 extra things. First, in Group 1's equation, we threw in D times 1 minus C2 to represent how much time Group 1 must spend teaching Group 2. During that time, they can't spend it working, so their work rate decreases. Secondly, we used a max function for Group 2 to make sure that the work rate is never negative. This is because, at minimum, they'd be doing no work, so it would be 0. The fact that the 3 other equations are percentages plays a role here, as that makes W prime also a percentage. This means that W prime represents how much of their max output each group is doing each day. We then use these equations to solve for W of t, or the total work done by day t. Note that all of our functions are unitless, meaning that W of t is also unitless, so W of t should only be used in comparison with other values of Wt.
Here are all of the constants we used in our equations. Note that these constants are defined for this particular model of astronauts on the ISS and may not apply to other situations. We declared G to be 43.7 days. We split the difference between the hours astronauts spend training for a trip to the ISS and the hours spent in simulators prior to the mission, both published by NASA, and converted this to days. T0 is 60 days, derived from a study that claimed stress desensitization takes 4 to 6 months. This is half of that lower bound converted to days. In the particular situation we're modeling, Group 1 had been there for about 5 months prior to Group 2's arrival, so we declared L to be 150. While Group 2's stay was planned to only last 8 days, it ended up being 15 days, so this is the value we assigned to F for our final time. We decided to make the short pause 5 days, 1/3 of the total time there, which would be enough to make a significant difference. We determined that 7 work units seemed like a valid halfway point in Group 2's capability growth, which we assigned W0. The remaining values were determined by what we found matched this particular situation the best. For all future slides, the graphs and data will be shown in this order, with the expectations on Group 2 being E sub 1, E sub 2, and E sub 3 from left to right. All 3 situations have fairly low stress as they've been at the ISS for so long. However, E sub 3 leads to the lowest average stress. The stress of Group 2 is significantly higher as they've just arrived. However, E sub 3 still leads to the lowest average amount of stress. As the amount of work done within the same range in all 3 situations, the capability graphs do not differ by a significant amount. The work rate of Group 1 is fairly high and constant in all 3 situations, but note the slight drop in their productivity once a very stressed Group 2 joins them in situation 2. As we'd expect from this fairly steady work rate, the total work done is nearly identical for all 3 situations, with the E sub 3 being only slightly higher. The work rate of Group 2 is much lower than Group 1 due to their stress. There is no productivity during the rest period in E sub 2, and with E sub 3, you can see the high stress and low levels of expected productivity cause them to only start being productive at around day 6. The work done by Group 2 in the 15 days ranges from 1.6 to 5.1. Combining the total work done by both groups, we can see that the immediate high expectations led to the highest total work done during that time, compared to the other 2 situations.
There are several limitations to the models we have created. By virtue of the fact that it is only a model, it cannot perfectly represent the situation. Firstly, we treated the groups as units, not taking into account the relationships and individuals that in a real situation would affect the productivity and stress within the groups. We are also limited to the factors of time, stress, capabilities, expectations, and total work done. In the very likely scenario that some other factors, for example fatigue, affect the groups, our model would not be able to accurately predict our outputs. Additionally, our parameters are very general and do not apply to specific cases. For instance, we take stress into account, but this stress may have a different effect depending on what kind of stress it is, what is causing the stress, and how it is affecting the person or groups feeling stress. Our models are able to show the general trends of stress, capabilities, and work, but if we were to try to find values at specific moments in time, the result would not be accurate. If we were to model this in the future to make it more accurate, we could enhance the tracking capabilities of our model so that it would get actual values for two groups' stress levels, capabilities, and work done. This way, one could reverse engineer equations based on the experiment's data points. We could also make our models more accurately represent specific scenarios by tailoring the parameters to specific types of jobs.
Here are all the sources we used in researching and developing our model, as well as footnotes for previous slides. Our preliminary equations were made using Desmos, and our final model was built and solved in MATLAB. We would like to thank the judges for taking the time to watch and review our presentation. Thank you.